Ladies and gentlemen, Damian Schenkelman. Thank you.
Thank you very much. Really happy to be here. It looks like a lot less people when sitting there. Believe me, it's a huge crowd. So my name is Damian Schenkelman, even though you can't see it on screen. I'm here to talk about getting over Moore's Law and parallelization in client-side JavaScript. Do you guys know why I can't see my slides? There we go. So this is me. I'm like the Ricky Bobby of development. I like speed. I like to understand why code goes fast. I like to understand optimizations, how the JIT compiler works, and all of that. So it came time for me to choose a topic for my kind of final work at college. And I was working with JavaScript. And since I really like parallelization and performance and everything, I decided to, well, I'm going to create a library that allows you to do operations like parallel map, parallel reduce, parallel filter automatically, so it wouldn't be on the developer side. And I ended up learning a lot about JavaScript and parallelization, and I want to share that with you. But before we delve into how JavaScript and parallelization in JavaScript works, I wanted to kind of give a contextual idea of why parallelization is important. So this is a pretty accurate description of Moore's Law. It's at scale. And basically, it says computer powered processor speed doubles over time. So if you have a processor 20 years ago, 18 years ago, it was twice as fast. Another way to look at that is the difference between graphics and games. I'm pretty sure the one on the right is more accurate. But nevertheless, the problem is that we're hitting an upper bound on Moore's Law. And that's because, well, we all know it. When we go to buy one of these, they don't come with 4 or 5 gigahertz in the clock speed. Instead, we get 4 cores, 16 cores, and so on. So we as developers can't be lazy as we were like, I don't know, 5 or 10 years back, because our applications won't get automatically fast by just changing the hardware. We need to take ownership of this and figure out how to make use of all of these cores to make our applications better. So why is this important for me and for JavaScript? This is like, seems like low level, but well, it kind of isn't. If you recall the Gmail interface for 2010, it was kind of one of the coolest apps. And if you think about its programming model, I have that nicely drawn user over there. It's mostly based on clicking buttons and doing stuff, and then just a bit of processing and doing AJAX requests, asynchronous I/O. So JavaScript asynchronous nature and how the event loop works are really useful for this kind of application. The thing is that now we have games running with JavaScript, ASM.js, and Firefox, and Unreal Engine, all that kind of stuff. And games have a very different programming model and usage of the CPU. As you can see here, the rectangles, which represent processing in the CPU, are much larger, and that's because games have to take into account graphics generations, physics simulations, and also how the AI is moving. So think of it as if you're playing a game, like, I don't know, Counter-Strike or Half-Life on a laggy network, and you got killed before you even heard the shot that killed you. You would be, like, really unhappy, right? So you want to be able to do all this stuff before the user kind of notices that there's a delay. So you need to kind of be faster than what we are right now. One of the options for that is that we can, well, split the bars. If we were doing some work in one thread, then we can use multiple threads and do that work in parallel. One other option, and this kind of looks weird, but we'll delve into that later, is to actually figure out how to make the bars shorter. And yes, sure, it looks like a trick here, but you can make them shorter. So let's take a look at the first one, which might be the one we're most familiar with. So this is web workers. Has anyone used web workers here? Yes, the same thing happened in the previous conference. I didn't get a lot of hands up. It's kind of demotivating, so I'm going to change the question. Has anyone used JavaScript here? Yes, awesome. So web workers and how they work. You create a new worker, and you specify the file that you want to run. And that worker is allocated into a thread, and you get a whole new event loop, exactly like you do when you are in the browser. The thing is that you can't access all the APIs, like the DOM. But, well, we can't access DOM, but we can do a lot of pretty cool stuff. We can pass messages between the UI thread and the worker thread. It's always asynchronous. There's no sharing of memory, but you can do stuff like say, okay, I want you to start doing some work, and the worker will do it. Let's dig a little deeper into the post message interface, because this is kind of the key to parallelism in JavaScript. So the first parameter, it's any message. You can send an object, you can send an array, you can send integers, etc. Just it's not anything. You can actually send exceptions, but well, there are other stuff there. But the important thing is the second parameter. So it's something weird. It says optional sequence of transferables. So let's dig into that a bit deeper. Optional means you can either send it or not. It's self-explanatory. Sequence is a JavaScript array. And transferable, and here's the tricky part, is the backing buffer for a JavaScript-typed array. So JavaScript typed arrays, like that doesn't really seem like what I know from JavaScript. Well, it's actually true. So you can create a typed array. You don't need to always use floating point IEEE 75.4 arithmetic. And you can store, for example, in this case, unsigned integers in there. If you try to store a double, then you lose the floating part. If you try to overflow, that it will do so, and you'll get, instead of -1, the highest positive value. But the interesting thing about buffers is that it's similar to the memory, and the array is a pointer to that memory. So you could have two different arrays pointing to the same buffer. In this case, if I had like the largest integer, and I point to it with an array of 4 bytes, then I would be able to look at each of those bytes. Now that we cover something that's kind of weird in general for JavaScript developers, we can kind of continue as if these were normal, regular arrays. So if I create an array, I told you before, I have two options. Either I can transfer the buffer for the array or not. That's the optional parameter. Well, if I don't, I'm doing cloning. Cloning means that every element of the array is individually cloned. A new copy for that is created. Like, imagine if you are serializing JSON and then deserializing it. You would be creating a whole new object, and a new array is available on the worker thread. Well, that's good because it's kind of immutable, and we have all heard the hype for that and stuff. But it's a problem if you have arrays that are like huge, because you have to copy each element separately. And that's really bad for when you're trying to do like high performance stuff. So the other options is using transferables. So what you can do here, and you can see the difference hopefully on the screen, is I'm sending a second parameter, which is the set of buffers that I want to transfer. In this case, it's the buffer for the array that I just created. And what that means is that I will no longer be able to use the array in the UI thread, but it will be automatically available in the worker thread, and it won't depend on the amount of items that the array has. It's kind of copying a pointer, so it's much faster. To think of it kind of having some raw numbers, well, the benchmarks, you can read the code there and the browsers that I run this into and stuff, but it can be like 90% faster to do transferables than to do cloning. And of course, this changes depending on the amount of items that you have. So let me show a couple of quick demos so you can actually see this live. So over here, I'm running a worker, and I'm going to create a small array. And that array has 100 elements. I'm going to create a large array, and that array has 250,000 elements. So first of all, I'm going to transfer the ownership. I'm going to post message the small array to see how much time it takes. And Well, it's almost a millisecond. If I do it again, it will be faster because the array, the worker has already received the message, so it's warmed up. But let's take a look at what happens when I post a large array. Well, it takes a lot longer, and that's expected because it has a lot more items. So what we want to do is to get that out of the equation. So if I actually assign the large array to a variable, I can post message it and transfer its buffer. And yes, it's much faster. As you can see, it was faster than even transferring just those 100 elements, and I'm transferring much more. There's, as I said before, a small drawback for this. If I try to do this again, anyone care to know what will happen? Well, it's an exception, because I don't have that array anymore, so I can't actually transfer it again to the worker thread. So we see how we can actually pass things to workers in a very fast manner. The only drawback is that we can pass them only once, and unless we get them back, we can't pass them back again. But workers are not only useful when you do parallelism. Imagine if you're trying to upload a picture to a server and you want to save bandwidth, so what you do is you try to compress that picture or that video or whatever before you send it. So compression is a CPU-bound task. It means that I'm not actually doing asynchronous I/O. I'm spending CPU time crunching numbers and figuring out how to compress each of the bytes. And in that case, what happens is that this is a good fit for web worker. I can say, okay, web worker, compress this image for me, and the UI thread will be able to continue to receive different messages from the user. So I'm going to compress a really large image. That's a BrazilJS site. And I can see that I can choose the site again, and I can send the second image to be compressed. So what happened is I sent the first image to be compressed, continue working on the UI thread while the worker did the compression. I sent the second image, and after that, both images were completed. So workers, in case you're not doing something like games or stuff, are still useful if you have a business application with some kind of requirement that needs you to kind of hold the CPU for the UI thread for a long time. So now that we're over with web workers, I want to show you kind of a case study. Now we kind of get the basics. So BrazilJS is the library I created for my final job. And as I said before, you can do things like parallel map. So parallel map represents fairly easily some image transformations. So for example, if I want to change its picture and its brightness or something like that, I can just modify it individually, and I don't need to have references between pixels to do that transformation. So the way this library works is that from the UI thread, you have that white array. And imagine that you have 4 cores in your machine, so it's conceptually separated into 4 different parts. What we have to do is split that array into parts, so we can transfer each of them separately to a separate worker. The worker does the job and then goes back, and the results are merged in the UI thread. The problem with that, as you might have guessed, is that it takes a lot of time for copying these elements. So you probably can't read this chart in the back, but the gist of it is that if you have 1 million elements in the array, this is only 1.4 times faster. It should be 4 times faster. It's 1.4 times faster. So there's a lot of room for improvement here. And I'm going to show you how JavaScript Future proposes to make this better. But before that, let's kind of change the subject. It's t-shirt time. So I have some t-shirts, and I'm going to throw it to different sections, starting from there. So t-shirt 1. Oh, I need to throw stronger. This is agile t-shirt throwings. For those who haven't done it, you adjust on each iteration. Okay, one there. I'm going to save the next one, one for the end of the presentation. Oh, that should. Can I throw that again, please? Just kidding. So we're all a bit more relaxed. Let's go back to parallelism and stuff. SIMD. So, well, this is making the bar shorter. How do we do that? Well, whenever we think of a computer, we are thinking of what's the system model. Let's consider an assembly instruction, for example, add. it takes 2 registers and stores the result in a third one. Well, what if we could do something different? What if each processor instruction did the addition, but instead of doing it in a single register, it had like an array, a register array, and it could add all of those at the same time? Well, it's kind of intuitively faster, and it could be an improvement for games, physics calculations, cryptography, and also improve battery life because you're using less CPU cycles to do the same amount of work that you used to need more for. In particular, for ECMAScript, there's an implementation, and this is kind of a proposal for ECMAScript Future, I think ES7, and it's also available, and you can play with this in Firefox nightly. So how does it work? You have, first of all, it's SIMD for 128 bits, so each set of instructions could be different, and 256 bits requires a different set of processor instructions, so that's not supported, at least in the current version of the spec. But you have 16 bytes. You split those into 4 different kind of lanes, 0 to 3. And each of those can be modified independently, but also when you do operations on them, they all happen in the same instruction. So a quick example, I create these float objects using the SIMD module that's available in Firefox Nightly. And I can do add. And, well, we don't have any operator overloading, so add is the best that we can do instead of using the plus sign. But that's automatically optimized by the compiler, the JIT compiler, JavaScript runtime, to a single processor instruction, and, well, it's much faster. How much faster? Well, let me show you a quick kind of real-world example. So here I have the real-world example, the sum of the elements in an array. Just take a look at the kind of the color difference in each row, and you will see that the samples are very similar. You don't need to make a lot of changes to start using SIMD. However, the performance is fairly different. I've only made like small tweaks, and I got it to be like 70% faster when using SIMD than when not using it. And, well, ideally, it would have been like 75% faster, 4 times as fast. But, well, there are some other things into play. But consider the power of this. Small changes, huge speedups. Let me show you a couple of demos. These are from the Intel and I think Mozilla team about how SIMD works. So let me refresh that. Flappy Bird, I think everyone's played it. It's a bit of a vicious game. So all the birds are doing thorough calculation. It's a physics simulation and stuff. So that's where the CPU power is spent. And what this is trying to do is it's trying to create as many birds as it can while keeping 30 frames per second. So as you can see, it's 350 and we've hit the limit. So when I turn SIMD on, more birds, the blue ones, start to show up. And that's because, well, we have more processing power available, operations are faster, so we can create more birds. You might be wondering, why don't we get 1,400 birds or something like that? Well, the physics simulation is not all this program's doing. It's also rendering and doing other stuff. So we are not actually optimizing all of it by 4x. It's just a small part that we can optimize. Another cool thing is that you can use web workers and SIMD together to get like huge speedups. So this is a Mandelbrot simulation. It's displaying a fractal. It takes more time to display that. The more black it has on screen. But you can see it's between 12, 16, perhaps 18 frames per second when it's on the back. If I turn on SIMD, this calculation is faster, and we can get 60 frames per second, 40. It's much higher. In this machine, I have 4 cores, so I can create 4 workers. And I get this huge speed up combining SIMD and web workers to get almost, I don't know, 13, 14 times more frames per second than we initially had. So that's huge. I told you before, so going back, we had web workers. We were trying to share them, but we had the problem of trying to send the array, and when the array got there, you couldn't send it again. Well, there's a proposal to kind of work around this in the future, but before we do that, and in topic with this we're going to go back in time. If anyone hasn't tried the Oculus Rift there, I highly recommend it. So going back in time a bit, there was this thing called Parallelization. It was an Intel project, and it was pretty similar to what my thesis did, of course, much better. It's a guy from Intel. But they allow you to do array map, array reduce, and all those operations, and they would take care of the parallelism inside of the library. The thing is that, unfortunately, this has been canceled. Brendan confirmed it to me, and Brendan is like truth word JavaScript, so this is canceled. He was kind enough to answer, and he provided a lot of links of what I'm going to show next. But I was really unhappy that that was canceled. But if we go back to today, well, there's kind of a new proposal for that, and that's shared array buffers. So one of them, the previous one, had the option of sending the buffer, that's the regular array buffer, and you couldn't send it again. In this case, that second line won't error. You will be able to share the same buffer across many workers. And that's huge, because all of those workers will have a piece of shared memory that they don't have to transfer between them anytime they want to do an operation, so things can work much faster. Of course, there's kind of a small drawback, or small depending on how you consider it. If you have shared memory, you need synchronization primitives. So this will require the addition of some synchronization primitives to make sure that you're not actually accessing the same piece of the array in two different worker threads. Nevertheless, for the case of BrazilJS, which was my library, since I'm doing a map, that's a trivially parallelizable operation. It means that I can operate on each element individually and on a portion of the array separately in each worker without the need for synchronization. And that means that I can do things much faster because I don't need to synchronize, and I also can share the memory like I couldn't do before. So I'm going to show you a quick demo of that. This is a really large image, zooming out. And this is running the same transformation that I showed you before. It was 1.4x. And when I run this in a single thread, I get like 208 milliseconds. When I use all my threads, I get 123. So if you do the math, that's like 1.6x, 1.7x. So it's a bit faster, and it didn't require a lot of changes to the code to support shared array buffers. But that's not enough. The thing is that we also need to take into account JavaScript's optimizations. I'm just running this once. So when I start to run this a lot of times, using tools like JSPerf, I get a huge speed up. We got like, it was 2.4x for a middle element. So we went from 1.4 to 2.4 by just adding support for these shared array buffers. Of course, 2.4 is not that close to 4, but there can be two different things. We have improvements to do to our library, definitely. And there's also probably room for improvement on Firefox side. This is still very experimental. It was made available in Firefox nightly just as a playground. But there's probably a lot more optimizations that the smart team there will be able to do to make this faster. So Brendan usually says this, but I'm presenting before him, so I get to do it. Always bet on JS. At least you can see that there's some huge things coming up in the parallelization space. These are some credits for different things, ideas for the talks, links, lemons. These are the links. You can check them out later. That's the link for the talk. That's my Twitter handle. You can reach me out and if you have any questions. And I have 2 more t-shirt times. So I didn't get all the way over there. Let's see if it does, this one does. I have to try it twice. Oh, yes, we have a proxy. Shoot. That's the problem with having 7 t-shirts and 3 sections. There we go. I'm out of t-shirts, guys. Sorry.